For the robotics project, we've studied robotic manipulators, both in the kinematic and dynamic side. This is done with the end goal of applying a linearized model predictive control. The first part of the study carried out involved path planning, both in the joint space with cubic and trapezoidal profiles and in the workspace by helical trajectories. The second part involved the study of inverse kinematics for 3 different configurations of robotic arms with 4, 5 and 6 degrees of freedom. Closed form kinematics was studied for non-redundant tasks, while for kinematic chains redundant to the required task, the inverse kinematics was solved by an optimization problem. The kinematic study carried out up to this was done with the goal of then providing a trajectory in the joint space along which to linearize the dynamic model of a 4DOF arm in order to formulate an optimal control problem via MPC formulation. This interface was written entirely by us within the project. 2 3D printed models were also produced in parallel, of which the 6DOF arm was also entirely designed by us from a mechanical point of view. For the remote control of the robotic platform as well, a web server was also developed to allow remote connection via Raspberry Pi, which allows for a standalone platform that can also be controlled remotely.
So we started with this robotic arm model from How to Mechatronics. It's a 5 degree of freedom robotic arm with a wrist which can yaw and tilt, it cannot roll. It's very lightweight and it's made without using a single ball bearing. All of the joints are mounted right onto the output shafts of the servo motors, which makes it not very rigid and not too reliable for robotic arms. So we decided that we could do better. We set out to build our own 6 degree of freedom robotic arm from scratch with our own end effector using the same cheap servo motors, but of course adding some considerable ball bearings to make the entire assembly more rigid and reliable. Here it is. This is the gripper. Then the 6th joint, this is the 5th joint, and now the 4th joint. All 3 of these make up the spherical wrist. Now you'll see the arm, the 3rd joint, and the 2nd joint, which are almost the same, which simplifies assembly, and finally the 1st joint, which uses 2 deep groove ball bearings to handle the considerable axial and radial combined loads that the base sees when the arm is used. Sadly, we would soon come to see that we made our arm so rigid that the internal PIDs of our servo motors were not sufficient to keep it stable, and they now became unstable, diverging, oscillating PIDs, as you'll see.
In ciabatte e si vola. Easy man, easy. Servo 1. No, please. I'm not shooting. Yeah.
And with an arm so rigid, look at the impact that the inertia of the gripper can have on the arm after an abrupt stop.
Show me what you did.
What you did?
What did you do? What is this? You broke the gripper.
I broke the axle.
What did you do?
I broke the axle? No?
You broke the axle of the gripper.
It's at this moment we realized it is not that easy to create a robust robotic arm. But at least, the gripper still works. Let's now look at the control, simulation, and MPC part of the project.
The first step to create and solve the MPC problem is to import the variables related to the robot and those needed for the solver interface, and after that we can proceed by assigning an initial guess based on a static arm balance to the first step. After this is done, the MPC interface written by us is called. Within this, the linearized model will then be evaluated, and the state matrices defining the constraints of the problem will be created. This optimal control problem will then be solved using the quadprog function built into MATLAB, which allows us to solve quadratic optimization problems. Even for complex trajectories in space, it's possible to solve the system in real time. From the solution of this problem, we can obtain, as we can see in this example, position, velocity and torque profiles for each of the joints. Through specific toolboxes, it's also possible to plot the robot in 3D, accurately representing the solution provided by the solver visually, implementing the dynamic model that calculates at each step, from the previous state and the current torque at the joints, the next state by integrating the model.
To drive the joints, a simple position control was adopted using servo motors. Servo motors achieve an angular position proportional to the PWM signal used to drive them. Furthermore, to emulate an industrial production environment, motor control and robot control were delegated to two different hardware components. An Arduino Uno or Mega was programmed to be in a constant state of polling, listening to potential values of a joint position vector coming from the UART connection, ready to convert this position to the appropriate value of duty cycle used for the PWM signal of the motors. A Raspberry Pi instead was used to compute the whole trajectory using inverse kinematics and then sent it with the appropriate timing to the Arduino as discussed above. To program the two boards, a model-based approach was employed, using respectively a full executable and algorithm export of C99 source code. Finally, to provide a way for the user to interact with the robot, we created a software platform in Python running on the Raspberry Pi. A Flask web server was then used to make the platform accessible to the local area network of the robot, as a way for issuing different types of command for the robot via a convenient web page.
Take 5.
No, 9. Wait, what 9?
For the robotics project.
Do it again.
For the robotics project, we've studied.
What did we study? Did we study?
For the robotics project, we've studied robotic
Something jigsaw you!